Okay, what you see in front of you is a list of data. The L1 list is our explanatory variable, or the X value in this case, which is the number of beers someone has had to drink over the course of, let's say, an hour or some fixed amount of time. Okay? List 2 is their blood alcohol content taken a half an hour after they finished drinking the beer. Okay? Now, what would you expect in this case? You would expect that the number of beers that someone had to drink would have an effect on their blood alcohol content. Okay, you'd expect that to be true. So the first thing I want to do in a situation like this is create a scatterplot and see, are these things related? How are they related? Are they related in the following way? As X goes up, does Y go up? Is that possible? Or as X goes up, does Y go down? Or as X goes up, does Y not respond at all? Okay, so this last case sort of might seem uninteresting, but what that would tell us is that even if X changes, that Y doesn't vary at all. Now, in this case, if you know a little bit about drinking beers and blood alcohol content, you know that most likely it's going to be that scenario up there. Now, I just realized I said something incorrectly. Well, I said it correctly, but I wrote the wrong picture. Yeah, I take complete responsibility. All right, so let's take a look at this. We'll go to our calculator. The data's already there. So there it is. So you want to create a scatterplot. So to do that, you do second y equals. Go to Statplot, hit enter on the first graph. And the first type of graph is the one we want. That's a scatterplot. That helps you compare two quantitative variables. Our x values were in list 1. Oop, hold on a second. A little slow to respond here today. Second L1, enter. And then second L2, enter. There you go. Zoom 9. I did this again. We'll do this. Here we go. Zoom 9. And here we are. We've got a reasonable picture of our data. You can kind of see it. And it looks positively associated. It looks like as X goes up, Y goes up. And from the look of it, it looks like it might even be linear. Looks like a line might fit that data pretty well. Okay. So what we could do now is find a linear regression for this set of data. So we'll go to Stat, go to Calculate, and let me make a comment just in terms of the AP exam and so forth. Most of the times when we use linear regression, we've been choosing number 4. There it is, linear regression, AX plus B. But on your AP exam and in the book by Yates, usually it's written A plus BX. Okay? So we're going to select that. It makes no difference, really. You'll see what I mean. So L1, comma, L2, enter. And there's our line of best fit. Let's grab this. So here you go. Ready? What do we know? Y hat equals A, which is negative 0.0127, plus B, which is 0.01796, X, where X is the number of beers, and Y is the blood alcohol content level as a percent. If you look at the statistical reference tables that are given with the AP exam, it says this on the second page: Y hat equals B0 plus B1X. Okay? So B sub 0 is your y-intercept, and B sub 1 is the slope. You'll also notice later in the page there, you'll see B1 equals the correlation times S of Y over S of X. We won't use that today, but this is an important formula to keep in mind. It helps you out of a lot of multiple choice style questions. Okay, so let's just stick to this order. So if this is A plus BX, this is B. All right. So here's the comment I want to make. I want you to think of this slope B as the following thing. I want you to think of it as sort of like a sample slope. And here's what I mean by a sample slope. The data here, which represented number of beers that the person had to drink and their BAC level, represents a sample of, I think there are 16 data points, so N is 16 in this case, out of a population that was really large. Let's pretend this was at a particularly big college or something, right? And so if it was at a big college, maybe the college has 25,000 students. So we'll just say that. So the population of everyone at that college, that would be all 25,000 students, right? If we had the time, we could have given all of them a certain number of beers, measured all their BAC levels, and created a scatter plot on our calculator that had a lot more stuff in it. It would, instead of having just 16 data points, would have had 25,000 data points. Okay? But if I had every data point, I could find, if I wanted, okay, so let's make it clear. If we had every data point, we could find the true slope for the entire population. Okay? Now, when you do that, usually you call that slope. That slope is usually denoted with this letter. It looks like a B. It's called beta. Okay? So what I want you to think of is that our slope, which was B equals 0.01796, is an estimate for the true slope of the entire college population that is usually denoted with the letter beta. So now, the question might be, is this. We suspect that the number of beers someone has to drink would have effect on BAC level. So we'd like to figure out a way to test this, get a significance test, get a result, and find out, is this true or not? Okay, so we can actually do that by starting with stating some hypotheses. So let's start with an HO and an HA. Now beta is going to represent the true slope for the entire population of all people at this particular college. And the question you want to ask yourself is if drinking beers has nothing to do with your BAC level, then what should beta equal? So 0. And the reason that's true is because of this. If the slope of a line is 0, here's your x value, your variable, and your y variable, then your scatter plot just sort of does whatever it does. And what you can't seem to figure out is you don't see any trend or a change in y when x changes. That would mean that x has no effect on y. Okay? All right? Now, in this case, I think we suspect that the true slope is going to be something positive, that as the number of beers you drink goes up, right, that the number of, the blood alcohol content level also goes up. So just like any test, after you've stated your hypotheses, you go to work on assumptions or conditions. So assumptions and conditions, that's always the second step. So what are the things that we need to check? Okay? Number one, you should sort of reason that the scatter plot shows a straight or a linear pattern. And it might not be perfect, but if we look at our scatter plot, this looked pretty linear, right? So that's good. So that's number one. You should really check that. Number two, you always want to check independence. So is the population greater than 10 times our sample size? Well, I said that this was some kind of college that had about 25,000 students in it, and 25,000 is certainly bigger than 10 times 16. So check. That means that the independence part of our assumptions are okay. All right. Next thing we need to do is this. This is a little strange. Okay? But for a given x value, or for any given x value, I should say, the y values vary normally about the least squared regression line, the LSRL. Let me draw a picture to kind of demonstrate this. This is often a little bit difficult to check, and in most problems you'll just be told, hey, assume this works, if this is true. But here's what they're basically trying to tell us. Here's your x and y axis, and here's your scatter plot. Here's your scatter plot of points, which looks something like this. Okay? There's a least squared regression line going through those points, maybe like that. And what this condition is telling us is that for any particular x value, for example, we pick like maybe x1 here, that the y values, most of them would be close to the LSRL, And there'd be sort of like a little normal distribution here for all those y values. This is my attempt, this very poor attempt to show a normal distribution on top of a line. But most of the y values would be really close to the LSRL, and then a few of them would be pretty far away. We'd expect some normal distribution of the y values if I added more data points. It's a big if there, if I added more data points. And then the same thing should happen for any x value. So if you went down here to x2, you'd get a copy of that normal distribution. The only difference would be is it'd be centered at a higher y value, because that y value here is higher than the y value here. All right? So that's an assumption. And then there's another one. The last assumption is this, that the standard deviation or variance of the y values stays constant. So what that basically means is this. Back in this picture again, if I added a value x3 here in between the other two, then you're not allowed to have this happen. You're not allowed to have a normal distribution that's much more spread out than the others. That's not supposed to occur. Okay? Again, checking this condition is difficult. We're just going to write these down and say these are the conditions that need to be met. And almost every problem that you're presented with, they'll say those conditions have been met and everything will be fine. So after you've checked your assumptions, usually the next step is to actually go calculate your t-test statistic. Okay. So let's remind ourselves what t-test statistics look like. In the past, we had things like this, like t equals x bar minus mu over s of x divided by the square root of n. Right? That's what they used to look like. This particular one is for a one sample t-test. There was another t-test statistic for a two sample t-test that we looked at. Okay. Well, you needed to know your sample mean, which you'd find using your data. You'd need to know whatever HO told us, whatever the hypothesized mean was. And then this thing had a name. This was called standard error. Okay? And that's what you call the standard deviation of the t-distribution. Well, for a linear regression t-test, it looks very similar. You're right, t equals, we're trying to test for slope. Our estimate for slope was b minus the hypothesized HO, the hypothesized population slope was 0, over, and on the bottom for the time being, I'm just going to write standard error sub b, the standard error of the slope. So the question you should be asking yourself is, how do we get SE of b? All right, so I will promise you that for most problems, it will be given to you. I'll show you how to calculate it, well, actually, maybe for the sake of argument, I'll tell you what it is in this case, and then after that we're done with the problem, I'll tell you how to calculate it. So it turns out, with the data that we were given, that the standard error for the slope would end up being 0.00242. Okay, that turns out to be what the standard error of the slope would be. If we remember, let's just go back for a minute, our least squared regression line had this equation. There it was. It was negative 0.0127 plus 0.01796x. So that makes b equal to 0.01796. And so now we can get our t-score. Our t-score is 0.01796 minus 0 over the standard error for the slope, which for the time being, you're sort of wondering, hey, where did you get that? I'm holding off on telling you. I'll tell you shortly. Okay? Yes, it's a little bit complicated. All right. So now we need to divide this and get a number. And I promise you, you'll get something actually pretty big. You're going to get about 7.48. Okay. All right. So in order for us to make sense of a t-score, now you might already know, hopefully, that this is many standard deviations away from the mean, and therefore is probably going to be significant. But if you take a t-distribution chart, what you need to do is find the correct number of degrees of freedom, and we haven't really talked about that yet. So for a linear regression t-test, the degrees of freedom is always equal to n minus 2, where n is the number of data points. So in our problem, we were given 16 data points. So the degrees of freedom is going to be 16 minus 2, or 14. So what we'll do is we'll look at our t-chart. We'll go to 14 degrees of freedom, and we're going to go across this row looking for that t-score of 7.48. Now, here's what will happen. You will make it all the way to the end of that row and find 4 something, I think. You end up getting 4.140. That's the last t-score in that row. And if you look up to the top, the p-value that goes with that is 0.0005. So now we know for sure that our p-value for our test is less than 0.005 because our t-score of 7.48 is beyond 4.14 standard deviations above the mean. Now we can finish off, because what we can say now is that we can reject HO in favor of HA. And what that means is that the true slope beta is really greater than 0, and that implies that as x goes up, y goes up. Or in other words, as the number of beers consumed gets higher, the BAC level for the subject will get higher. Okay? That's how you perform a linear regression t-test. Now, while we're at it, we might as well just tell you how you can get a confidence interval also. So let's do a confidence interval real quick. It's not that big a deal. So confidence intervals look like this. They look like B, which is your estimate for slope, plus or minus T star times the standard error of B. Okay? In my mind, in your minds, I'd like you to be thinking, for means, for example, the old confidence intervals we looked at used to look like this: x bar plus or minus T star S of x over the square root of n. But this is the same thing. There's the standard of error. There's the critical value of T. Here's your estimate for the mean. Here's your standard error. Here's the critical value of T. Here's your estimate for slope. So it's got the same layout. Our slope estimate from our regression line was 1796 plus or minus. I'll leave T star blank for now. The SC of B was 0.002402. All right. Lastly, for the T star, it depends on the level of confidence. Let's pretend we want a 95% confidence interval, which is sort of the most famous one. We go to degrees of freedom equals 14 in the table. There's a 14 down here. We look across until on the bottom you see 95%. Or the tail area on the top is 0.025. They would match up. That would go together. The t-score that you'll find there is 2.145. So that number goes in here, and then you can go calculate the confidence interval, which would be, let's see what that confidence interval would be. Okay, so the lower is 0.0128 to an upper value of 0.021 about. Let's say it that way. All right, so notice this confidence interval does not end up catching 0. We shouldn't really be surprised by that, because when we did our significance test, we found that the slope truly was greater than 0. So it sort of makes sense that this confidence interval would not catch that. I mean, our significance test was very significant, a very small p-value. Okay, so let's go back and finish one thing. You'll notice in this question I gave you what the standard error of the slope was. And I will tell you that in most problems, you can expect that to be given to you. So let me give you an example. We're going to go look at the 2000, one of the AP exams. We're going to look at 2001 problem 6, and I'm just going to go over where this data is usually found. So here you go. This is some data that was given to us in the problem 2001 problem 6. So some things to look for. First off, the first column is usually called predictor. Underneath it, the first word you usually see is constant. That's talking about your y-intercept, which is right here. It's the coefficient, 23.514. All right. So actually, if you wanted to, you can even write your line of best fit here. You could write y hat equals 23.514 plus the thing underneath constant will vary from problem to problem. In this case, they said GPA, which meant grade point average, but that's always your explanatory variable. And so, for example, the problem we had just done, we were talking about number of beers explaining blood alcohol content level. If we had a data summary chart like this for the problem we just done, it wouldn't say GPA, it would have said number of beers. The number next to that is the slope, so that goes over here, negative 2.7555, okay? So let me tell you about sort of a nice luxury that you can expect to have when you take the exam, and that is this thing given to us here. That number there, it says standard deviation, is actually the standard error of the slope. So they give it to you. Even nicer, next to it is a t-value. That t-value is actually had by, or can be computed yourself if you wanted, by doing t equals the slope of negative 2.7555 minus 0 over the standard deviation of 0.4668. You divide that, you will get negative 5.9 standard deviations below the mean. And then even nicer, you don't even have to go look that up in the t-chart because here's the p-value. It's basically 0 in the third decimal place. So you could tell me right now that in this particular situation, if we were testing the hypotheses HO, that the true slope, beta, was 0 versus HA, that the slope was not 0, it would be significant. And you would reject HO in favor of HA. So this is, like I said, what you can expect to be given. Again, that still doesn't answer the question, and that is, how did I, in this problem, know that SE of B was equal to the number I said it was, which was right here, 0.002402. Okay, so that's how we'll finish and go from there. So here you go. The formula for SE of B is usually written like this. SE of B equals S over the square root of the sum of all the x values minus the mean squared, where S is equal to the following: the square root of the sum of all the residuals squared over n minus 2, which is the degrees of freedom. Okay? Now, interesting enough, if I go back to that chart of data I just gave, when I just went over that problem and showed you where the information was in that chart, even S is given to you here. Just notice in the lower left corner you can expect to find S. That was found by doing the following: the square root of the sum of all the residuals squared over n minus 2, and then the square root of that quantity. So usually these problems are really nice. They tell you what these things are. In some rare event where you have to calculate it, this is what you would need to do. All right, so don't forget how you get residuals. Residuals are always observed minus predicted, y minus y hat squared. That's what that's going to be. All right, so we're going to do all of this in the calculator. The first thing we're going to do is go figure out what S is. So let's see if we can do that. So I'll go back to my calculator. I've already done a regression on the data. So the first thing you'd have to do in a case like this is go to Stat Edit, make sure you have your X and Y list entered, and then you'd have to go to Stat and Calculate and Linear Regression, L1, L2. Okay, so second 1, comma, second 2, comma, enter, and there you go. Okay, there's the information. You'll notice that this 0.0179 B equals that. That's your slope that we expected to get. All right, well, when you do this, the calculator creates the residuals for you. So if I go back to Stat Edit, I'm going to go to the top of list 3, and let's think about what I want to do to get S for a moment. So here's S. I want to take all my residuals. I want to square them, because that's what this exponent is telling me to do. I want to add them up. Oops, sorry, that looks sloppy. Forgive me for a minute. I want to add them, because that's a sigma. That's what that's saying. Then divide by n minus 2, which in our case is going to equal 14, because there were 16 data points. And I want to finish by taking the square root. So I'm going to do this in pieces. First thing I'm going to do is do the residuals squared. So in L3, I'm going to do second stat. I'm going to go up. There's residuals. And I'm just going to square. Press the x squared key. So there are all the residuals squared. All right. The next thing I want to do after doing that is I want to add them. I want to do the sigma part. Let's add them up. So let's do that. You do second quit to get out of this. You do second stat. and you go over to math. And the fifth thing on the list is sum. You see the word sum there? We're going to hit sum of list 3. Oop, there's a mistake there. Hold on, second 3. Here we go. So there's the sum of those things. We want to divide that by 14. And there we go. And the last thing we want to do is the square root. So we can do second square root of that answer. Enter. And we get this number, 0.02044. So 0.02044. So that's the S that would have been in the corner of the table that's over here if I had given you a whole table information for the problem we had just looked at. Okay, well, now we're not quite done yet because we need to take this value of S and divide it by that quantity. So let's take a look at that quantity for a minute. It's the square root of the sum of all the x values minus the mean of the x values squared. Okay, so let's go back to our calculator. We can do that. To get the mean of the x values, we can do stat, calc, one variable statistics of list 1, because that's where we had stored our x values. I hit enter, and there's the x bar right on top, 4.8125. So here we go. I'm going to go back to stat edit. I'm going to go over to list 4 here, and I'm going to try and be clever about things. Now my mean for the x values is 4.8125. So here's what we're going to do. We're going to do open parenthesis, list 1, which is where all the x values are, minus the mean, 4.8125. And we're going to square that. Okay. We'll hit enter on those. So there's all my deviations from x squared. I need to add those up, so I'm going to do second quit. How do I know I'm going to add it up? Because that's what the sigma tells me. So far, I've only done this part. Sigma is saying add all those up. So that's what we're going to do now. So I'll do second stat, math, 5, which is the sum of list 4. That's where I had all that information. Okay, I hit enter. And then lastly, I got to take the square root of it. Why? Because that's what this was telling me. Take the square root of all that stuff. That's what I need to do. All right, so I'm going to do that. So second square root of that number, the up arrow there, enter, and we get 8.511. Okay, great. So now we're actually ready. So 8.511. That's the bottom. The top is going to be S, which is 0.02044. Let's divide and finish this up. So 0.02044 divided by that answer, enter, and here we get 0.002402. Oh, well, that's a familiar number. So we just said that the SE of B is 0.002402. But that was exactly the number that we talked about earlier in the problem. Earlier in the problem, I said to you, hey, SE of B, here it is equal to 0.002402. All right? So now what you've seen is you've seen how we can go through the calculator and get that calculation. Chances are you won't be asked to do that, but you should at least know where it all comes from. Okay? One last comment, just so you know. This S in the corner here, this thing that we're finding out, is sometimes referred to as the standard deviation of the residuals. Okay? All right. Thanks for watching.